We are developing different types of photonic sensors, and I'm showing you examples of those that we're developing, and they are nanostructures. And we've been reporting that they are very nicely able to detect different types of volatiles with a single sensing structure. But the topic today is how can we make the devices like this as stable as ideal thing? It never is. Okay, crazy example or crazy ask, but we're working on that. Okay, so that's our basically 15 minutes. So the reason that we're doing that is that as you saw in previous talks, there are many volatiles that people would like to do the measurements of. And I'm talking that as opportunities for sensors or in general for detectors. You can see that the drivers and trends, they're related to different types of industries. And for the trends, this was accuracy keeps on coming again and again and again. Over time, that means you need to be accurate over long periods of time, as long as the maintenance cycle is. And the markets are quite significant. You can see they are in billions of dollars. And these two photos that I took are of non-optical sensors and optical sensors. So we will be talking today about the optical. For detection, for high quality detection, end users will choose what key. Okay, and in detection of air quality, ambient air quality, the 4 parameters of interest across all this planet is to detect ozone, CO, sulfur dioxide, and nitrogen dioxide to the quantities where you are reliably saying, yeah, these are the concentrations and this is the air quality factor. And in addition to these 4 gases, they also detect the particles. Okay. Now, the reason that I'm showing you these big machines, which are not sensors by definition, okay, because they work and people use them a lot, and if needed, they put them on SUVs or in the trucks or on the side of the road because they need this data. And of course, we can go on the internet for $5 or less. We can buy these sensors, and they got from big ones through many decades, like 50 years or so. Now they're very, they are not very expensive. They're very low cost, and poor accuracy is not a limitation. It's by design. They were not designed to do these types of measurements that I'm showing. Okay? Because they were designed to measure very large levels of signals in the presence of something else that is much smaller in the response. And those big ones, they were designed for industrial and residential safety to detect leaks of known things. Okay? If the leak is tiny, you don't care. If the leak is large, your signal is huge, and that's what you do. Now, these are the correlation lines, and these are the guesses from the previous slide. Now, you see these examples, and many publications also saying, look at my R squared. It's not very close to 1.0. Okay? They're not very close. Why? Because they are designed as a single output device, so they will equally well respond to more than one guess because they need to be reversible. Okay? So the interaction forces between the guess and the sensing material are not as strong as for the dosimeter. Okay? And that's why you can see some of the confessions in Nature and other publications that, well, be careful. Okay? That's what they say. Now, so going back to those devices from 2 slides ago, those are some examples of different technologies. Okay, and by design, they're not afraid of those complex mixtures. They're not afraid of my breath or my outdoor air or whatever, and they push the responses of different gases into different directions. This is my cartoon. So these days, they are still large in size, large as my coffee cup. Okay? It's and the part of that community. Right? Okay. So we have the machines that need the desktop space, but we have them as small as this coffee cup. That's a GC would be, and mass spectrometers that are, oh, this is the guy. Okay. And okay, if I'm $10,000, Zero Sciences used to be $8,000. Okay, so same cost, okay, for same price. And I'm sorry. But basically, what I'm showing here, look, this performance has been recognized by the community big time. So we're taking mathematics of how it's done and applying the new hardware tricks from this century to implement that mathematics into solutions that look in a very different form factor, and I would say skin or something. Okay, so mathematically, the single output sensors, the zero order devices, so they will have only one output. Without the intensity change, then if the window is dirty, I will never know. Or resistance change, if something is foul, I will never know. And so the first order and second order devices, they have one or more dependent variables. And in this way, you're not afraid of the known interferences you can correct, because maybe interference is only here, and that this is the gas chromatography run of a breath of a healthy human. Okay, and you can see this many peaks, and you can resolve the ones that you care about. Okay, so if you have two independent variables, then automatically you are really not afraid of in unknown interferences. So you don't need to calibrate for all the interferences that might happen in the practical use. Well, nothing is free. And this table shows that, well, you will have a person, technician, or whatever that person is called, to make sure that that machine works every day per spec. And this table says that, yeah, these machines and all others, they have the calibration frequency that sometimes it's once per use, or once per day, or once in 2 weeks, or whatever. So it's not something that is lasting for many years, as I'm crazy one. So I would like my sensor to work. Okay. So we also part of the sensing community, sensor array community. So this is my sensor of 4 elements, 24. There are more and more in literature. And the reason that I made this slide and this quote is that they are independently sitting on the sensor platform, and when they age, nobody knows the members how other ages, and that's how the independent aging adds to the overall prediction. I'm sorry, when I'm very fresh, then everything is nice. As soon as I'm from my pristine lab conditions, oops, something happens. And what that something is when the sensor, each element starts to drift, the total thing also gets out of not whack, but starts to drift more. And you can see the more elements in the sensor array, the more pain I will have in the field. So this year is 40 years of that, and every review article up to now says, hey, drift of the system is a challenge we need to work on. Okay, so our approach is that we use a single sensing element with multiple outputs, and here we're showing that we're working either in RF spectral range or optical frequencies, and my talk today is on optical spectral frequencies. And this cartoon shows that we are trying not to be afraid of complex mixes and push the responses of our sensor into different directions. Okay, so mathematically, we are pushing them in different directions. So if we have only one direction to push, that means that they will be as same as the single output device. So if we have 2 dimensions, like we saw in the previous talk, then it's a 2-dimensional dispersion. So the more dimensions we have, the stronger our sensor is to not to be affected by all kinds of interferences, and we can do mixtures as well. Okay, so you saw on the first slide different types of natural things or iridescent structures and fabricated ones as well. But the reason that we like those because they are open to air. This multilayer interference structure, open to air and air, different types of volatiles, they interact with different regions of this nanostructure. What we have learned some years ago is that when we expose this type of nanostructure to different volatiles, and this is our differential reflectance spectrum, it changes in a very unique, nice way, and it's different from different types of volatiles, even closely related ones. So when we are normalizing the response to air itself, then it's a flat line with the unity of 100% depending on what we. So what we learned over the years is that this exceptional selectivity to different volatiles with a single structure is coming from the reason that there is a chemical gradient from top to bottom in these nanostructures, and that allows the different volatiles to preferentially interact with different regions, and optically we detect that. So if we look at the reflectivity spectrum of a butterfly like this, then it's relatively simple, and you can see many more features in the fabricated structure. So we use different types of technologies to do that, and we develop the design rules for the selectivity control. On the internet, there are different types of machine learning tools. We're using our own ones. You can see that they're classic ones and also the new ones, because we need better improvement in stability. So if we use different types of gases, as you can see here, these are the different spectral features. And I'm pointing your attention to this first one. And the punchline here is that sometimes the spectral features cross this flat line. And that's important for the stability. And with our multivariate statistics, you can see that we're pushing responses into different directions. So we're better than different types of sensor arrays. And my cartoon shows here that the drift in the single output sensors goes unnoticed. Then we need to periodically recalibrate our classical devices. We love them. Okay? But why? Because they give us the accurate responses. But that's what we do. And conceptually, with our sensors, we don't need to do that. So to show one of the examples, we are looking at the reflectivity pattern, and these are the spectral features in the presence of CO2 and water. And the flat line is in air. When the run is pretty short, these are two replicates of this structure. So you can see exposures to analyte, interference, mixtures, and these are two replicates of these steps. And at different wavelengths, you can see that the responses to humidity can be either relatively large or very tiny. So over the time of the experiment, you can see that some of the wavelengths show this type of a baseline change, other wavelengths show this baseline change. So we're taking advantage of that, and we say, well, we'll apply conventional machine learning to a support vector machine. Yeah, awesome. And when we do that, when we calibrate on the first replicant, and then we predict the future in the presence of drift, conventional tool doesn't work well. So our new tool is much better. So my last slide shows that support vector machine changes that is unable to predict quite well. And you can see the changes. If I'm using the PLS, the prediction is slightly different as well. With our new tool, it's as good as you can see. So we're using this type of capabilities for not only room temperature sensing, but also for high temperature sensing. And these are the structures that we have for high temperature sensors as well. So to conclude, this is the reality that we're working towards. Today, my talk is on optical sensors. Tomorrow is on electrical ones. But basically, it's a combination of data analytics that without the excitation tricks and without the design, data analytics doesn't help. So that's my summary. Thank you.